Okay, so for the second case for this problem, so determine the allowable strength and the design strength of W18 by 35 for an A992 steel with the following cases. And for the case letter A right here, we have already solved for that in the previous video. And for this video, we would be solving for the second case, which is letter B. And in letter B, it is said here that the unbraced length is 3 meters and CB is equal to 1.0. Okay, so from that, since its unbraced length would be 3 meters, so LB is equal to 3 meters. Okay, so if we are to check these steps again right here, so the first step is to list the properties, and the second step is to check the compactness of the section, and the third step is to get the nominal flexural moment, and the first step in the third step is to get the plastic moment by FYZX. And as for 3B, we should check for the lateral torsional buckling if it is applicable by comparing your unbraced length with the values of LP and LR. And from steps number 1, 2, and 3A, we have already done that in the previous video. So from that, we would be proceeding to step 3.b. So once again, so for step 1, we have already listed the parameters from the previous video. And as for the second, we have already concluded that our section is indeed a compact section. So it is previously solved in the previous video. And our plastic moment would be 3760500 Newton millimeters. Okay, so the second step in the third step, so 3.p, we would be comparing our LB or the unbraced length with the values of LP and LR. So if you can remember in our first video, we would be comparing it with LP and LB for us to know what equations we would use. So if it is under zone 1, zone 2, or zone 3. Okay, so to save me some time in drawing this table right here, I would just be copying it and I would be pasting it to the last page. So I would be using this instead. And since it is said in the problem that the value of our unbraced length would be 3 meters, so our LB would be 3 meters, or in millimeters, that would be 3,000 millimeters. Okay, as for the value for your LP, so LP, so that is equal to 1.76 RY, 1.76 RY times the square root of, with RY, times the square root of E over Fy. So this came from the formula from the NSCP. So it would be this. So I would be copying it and would be pasting it here. So basically, it is this equation right here. And as for your LR, so erase ko na lang to. Yan na lang agad tayo. So that is for the value for LP once again. And as for the value for your LR, that would be this formula right here. So wait. So for the value for your LR, it would be this value right here. I mean, this equation right here. And your RTS, so for us to solve for your RTS right here, RTS squared, moment of inertia about the y-axis times your warping coefficient, CW. So you can get those both in the AISC database, divided by the elastic section modulus. So that is to be for RTS. So RTS. And as for RJ, we have already identified our torsional moment of inertia. So that is to be this. The value of C is equal to 1 for doubly symmetric I-shaped. And since your wide flange is I-shaped, so we would be using C is equal to 1. Okay, and as for our HO right here, so HO is actually equal to the distance from the centroids of both flanges. So if we are to consider this figure earlier, so your HO is actually this line right here. So from the centroid to the centroid of our flanges. So that is to be for HO. Okay, so from that, HO is equal to depth. So D minus thickness of the flange divided by 2 times 2. So ultimately 2 would cancel out. So basically that is just to be D minus TF. Okay, so first things first, let's solve for LP first. Okay, so I would just be moving this first to the next page so that we would be having spaces here. So for LP, so direct substitution, LP is equal to 1.76 times the radius of gyration about the y-axis. So our RY would be 31 mm. So 31 mm times the square root of E over Fy, and our modulus of elasticity once again would be equal to 200,000. And our value for Fy, which is the yield stress, would be 345. So our LP from that would be equal to, wait, nasan yung calculator ko? So 1.76 times 31 times the square root of 200,000 divided by 345. So the value of our LP would be 1,313.65 millimeters. So from that, the value of our LP is actually equal to 1,313. So 1313.65 millimeters. Okay. So as for this value right here, so for LR, so if we are to solve for RTS first, so let's just erase this part right here since we already know that C is equal to 1. That is according to 506.2-8A. So it would be this page right here from NSCP. So it would be this. So that is to be C is equal to 1. Okay, so for the other values for RTS, so tsaka na yun. Okay, so for our for our RTS, once again, that is equal to the square root of IY. And our IY is equal to 6.37 times 10 raised to 6. So 6.37 times 10 raised to 6 times CW, and our CW, or the warping coefficient, is equal to 306 times 10 raised to 9. Okay guys, by the way, we have a correction here in the given. So the section modulus here should be 994 times 10 raised to 3. But it really doesn't matter since we didn't use that in the previous video. Okay, so for us to solve for the value of RTS, so substituting known values, so our moment of inertia about the y-axis is equal to 6.37 times 10 raised to 6. So if you would be looking at it here, that would be IY. And as for our value for CW, and our CW is the warping coefficient, that is to be 306 times 10 raised to 9. So 306 times 10 raised to 9. And as for our value for our section modulus, so that is to be 994 times 10 raised to 3. So 994 times 10 raised to 3. So solving for this, so RTS squared, so that is to be equal to, so that would be the value for our RTS squared. So for us to get the value of our RTS, we would be getting the square root of this. So square root of answer is equal to 37.478. So 37.478. So that is for the value of RTS. Okay, so what else? So let's get the value of HO. Since our HO would be HO would be D minus TF, and our D would be 450 millimeters, and our TF would be, well, the thickness of the flange, that is to be 10.8. So 10.8. So from that, our HO would now be equal to 450 minus 10.8. So that is to be 439.2. So 439.20 millimeters. So this is to be the value for our H of O. Okay, so since we already have all of our values here, we can now solve for the value of LR. LR is equal to 1.95 RTS, and our RTS would be equal to 37.478. So 37.478 times, I will choose green. So I would be explaining this to you later why I am grouping it like this. So 200,000 divided by 0.7 times Fy, and our Fy would be 345. Okay, times the square root of, so let's choose another color, so JC, and our value of J would be 211 times 10 raised to 3. So 211 times 10 raised to 3. So 211 times 10 raised to 3 times C, and our C here would be equal to 1 divided by SX, so 994 times 10 raised to 3 times HO, and our HO once again is equal to 438.20. So times 438.20. So after that, times the square root of 1 plus square root of 1 plus 6.76 times 0.7 times 345 divided by 200,000 times 994 times 10 raised to 3 times 438.2 divided by 211 times 10 raised to 3 times 1. So that is to be SXHO divided by JC. All of this would be squared. Okay, so why did I write it like this? So it would be up to you on how you would be solving this very long equation right here. But just for me to show my technique, I to do it this way. So I would be solving for this, and I would be storing it in my calculator as A. And after that, I would be solving for this, and I would be storing it as B. So shift store B. And as for this, I would be storing it as C. So C. And as you can see here, so basically this equation right here, so this green part right here, is actually the inverse of this. So as you can see here, 200,000 divided by 0.7 times 345. And if you would be looking at it here, 0.7 times 345 divided by 200,000. So basically that is to be 1 over B. And this, and as well as this is actually 1 over C. So ultimately, for me to get the value of my LR, so that is to be A times B times square root of C times square root of 1 plus square root of 1 plus 6.76 times 1 over the reciprocal of your B and C. So 1 over BC. So B and C squared. So after storing these values right here, I would just input this into my calculator. So once again, it would be up to you on how you would be solving for this very long equation right here, but I am just sharing my technique. So for the value of A, 1.95 times 37.478 So equal sign. So shift store A. So there, na-store ko na sa A. And as for the second value, that is to be 200,000, 200, 1, 2, 3, divided by 0.7 times 345. So this is to be 828. So shift store B. So okay, meron na tayo sa B. And as for the value of C, that is to be 211 times 1,000 divided by 994 times 1,000 times 438.2. Shift store C. Okay, so since I already have my values of A, B, and C, I would now be inputting them like this. So A times B times the square root of alpha C times the square root of 1 plus the square root of 1 plus 6.76 times, so 1 over B times C squared. Okay, so after that, I would be pressing equal sign, and my answer here, LR, would now be equal to 3662.08 millimeters. Okay, so using this answer right here, I would now be concluding that my LR is to be 3662.08 mm. So meaning this limit right here is actually equal to 1313.65, and this LT right here, I mean LR right here, has a limit of 3662.08. So this would be your value for LP and your LR. Okay, so now that our unbraced length is equal to 3000 mm, it is safe to assume that we would be under zone 2. Why? Because it is greater than 1313.65 and it is less than 3662.08. If we are to consider our problem to be under zone 2, we would be using this equation here. So this equation right here. So this is for zone 2. Okay, I will just be writing this. So zone 2. So this is actually in page 5-64. So it would be in the lower part. And that is to be equation 506.2-2. Okay, so for us to get the value of mn for the second problem, so mn, and that is equal to our CB, and our CB from the given, that is to be 1.0 times our MP. And what was our MP once again? So our MP is equal to 3760500 minus 0.7 Fy, and our Fy would be 345 times Sx, and our Sx once again is equal to 994 times 10 raised to 3. So 994 times 10 raised to 3. And from that, we would be multiplying this. So since I don't have any space, I would be moving them to the left. So wait. Okay, so times this. So LB minus LP, and our LB and LP is 1313.65 and 3662.08 respectively. So I would just be copying them for me not to forget. So there. So LB minus LP. So for my LB, that is to be 3000 mm. So this is the unbraced length minus LP, and my LP is 1313.65, and my LR is 3662.08, and my LP is equal to 1313.65. Oops, by the way guys, we have a correction here. So this should be 376050000. So as well as this. So nagkulang tayo ng 0 dyan. Then, okay, so are we good to go? Oh, by the way, we should have another parenthesis here. So this value right here should be multiplied by this right here. And this is to be the closing bracket. So solving for that, for our mn, so mn is equal to enter, and our answer would now be equal to 278392452.8 Newton millimeters. So 278392452.8. Okay, we'll just be erasing this since I don't need this anymore. So if we are to convert this into kilonewton meter, I would be dividing it by 1000 and 1000 once again. So 10 raised to 6. So from that, our answer would be 278.392 kilonewton meter. So this is to be our mn. So for us to solve for the values of our mu, so mu is equal to VMN. Sorry, VMN. So this is for LRFD. So our mu would now be equal to 0.9 times 278.392. So ultimately, our ultimate strength, or our design strength I should say, is equal to, so we would be multiplying this by 0.9. So that is to be 250.55 Newton meters. So this is to be the design strength. And as for the allowable strength, so MA, that is to be Mn divided by omega. So ASD. Okay, so solving for MA, or the allowable flexural strength, that is to be 278.392 kilonewton meter divided by our value for omega, which is 1.67. So for our allowable flexural strength, that would be equal to, so 278.392 divided by 1.67, so that is to be 166, so 166.702 kilonewton meter. So by the way, I have forgot our unit here, so this should be kilonewton meter. So that is it for our second case, which is the unbraced length is equal to 3 meters.